Hello. This says it's Unit 2, but it's actually kind of Unit 3 because this is the third unit that we've done. This will be the last one that we do this 9 weeks. It's on electron configuration, nuclear chemistry, lots of fun things. I think you'll like it. So let's get started. You should have your notes with you. Today we're going to learn how to write electron configurations. In order to do that, we have to talk to you about the quantum mechanical model of the atom, which sounds a lot more complicated than it really is, so I wouldn't worry about it. Just to review, I think you guys know how to do a Bohr model of the atom. You guys drew them in 8th grade. They're kind of useful, actually, but they're not exactly the way that atoms are put together, which shouldn't surprise you any. But let's review how to do Bohr models, and we'll talk about a few things first. Valence electrons. What are valence electrons? Well, valence electrons are the electrons in the outer energy level of the atom. So whatever's the outside most energy level. Remember, we're calling them energy levels, not shells anymore. Outermost energy level of the atom, the electrons that are out there, those are going to be the valence electrons for that atom. Those are the electrons that are 100% responsible for bonding, for any chemical bonding that occurs. We also need to talk about the octet rule. The octet rule, octet is 8. So the octet rule states that atoms are going to lose, gain, or share electrons in their outer energy level in order to get a full set of 8. Now, why do they want 8? Well, because the noble gases have 8 and they're extremely stable. So atoms become very stable if they have 8 valence electrons. So they're going to do whatever they need to do to get those 8 valence electrons. The Bohr model of the atom is not really complete. It kind of gives you the impression that electrons travel in these perfect little circles, like around a racetrack, and they don't. They actually move all over the place. So we have different models of the atom that we use now that we know a little better. However, the Bohr model is very good for teaching, so we'll still use that from time to time. This was a little video on how electrons kind of operate, but for whatever reason it didn't want to play. Let's see if we can go back and play it for you. There we go, play that.
The cores of atoms tend to stick together, but electrons are free to move. And this is why chemists love electrons. If we could marry them, we probably would. But electrons are weird. They appear to behave either as particles, like little baseballs, or as waves, like water waves, depending on the experiment that we perform. The cores...
Okay, so there you go. So let's see if we can go to the next slide. There we go. So discoveries about electrons. A lot of people were involved at different times, discovering different things, and we kind of put it all together in something called the quantum mechanical model. So these are some of the scientists that are responsible for discoveries that led to this new model that we use now. Electrons have wave-particle duality. That means that they can act as a wave and a particle kind of at the same time. There's some real good, let's see, what was it? It was on Amazon Prime. There's a really good set of 3 videos, and now they're longer, about an hour long, that are called The Atom. And if you watch those are really, really good at explaining some of these very difficult concepts and the scientists who discovered them and how they discovered them. So they're very interesting if you ever have time to do that. But the concept that every elemental particle, like an electron, can be described in both as a wave and or as a particle at the same time. So limitations of the Bohr model. Scientific discoveries changed our understanding of what the electron really is and how it acts. So we needed a new model for describing the electrons and an atom. The Heisenberg uncertainty principle is something that we'll need to talk about because it kind of helps us get an understanding of these little elusive electrons. Heisenberg uncertainty principle says that you can't know both the location and the velocity of a particle at the same time. So that means while we might be able to guess where an electron is, we can't know how fast it's going. If we kind of know how it's moving, we don't know exactly where it is. So it's an uncertainty principle. Okay, it basically means there's a fundamental limit to how much we know about where an electron is and where it's going at the same time. As you watch the following video clip, please pay attention to how the location of electron is represented. Kind of fun.
One of the weirdest things about electrons is that we can't exactly say where they are. It's not that we don't have the equipment, it's that this uncertainty is part of our model of the electron. So we can't pinpoint them. Fine. But we can say there's a certain probability of finding an electron in a given space around the nucleus. And that means that we can ask the following question. If we drew a shape around the nucleus such that we would be 95% sure of finding a given electron within that shape, what would it look like? Here are a few of these shapes. Chemists call them orbitals, and what each one looks like depends on, among other things, how much energy it has.
Okay, so we're going to talk about orbitals and what those are. Our current model is known as a quantum mechanical model, and I've talked about that a little bit. On your left is the Bohr model, and on the right is quantum mechanical model. And what you'll see is it looks a little bit different. Those shapes that are inside are orbitals that are around the nucleus, and they kind of fit on top of each other like an onion, like skins of an onion. They fit on top of each other around that nucleus. The atomic orbital represents a three-dimensional region around the nucleus where an electron is likely to be found 95% of the time. So it's an area of probability. Okay, it's not a certainty, but it's a very likely probability that we will find an electron in this particular shape, depending on what atom it is and what electron it is. We can determine pretty close where that electron will be found. 0 to 5% of the time, it won't be there when we think it's there. But it's, again, an area of probability. Probable location, because electrons have that wave-particle duality, and we can't know exactly, because of Heisenberg uncertainty principle, we can't know exactly where they are and what they're doing at the same time, so we kind of have to guess that probable location, and that's called an atomic orbital. Energy levels, okay. Energy levels, principal energy levels are the atom's major energy levels. Now, you're used to thinking of shells, okay? We're going to think about them as orbitals now. Okay, the energy levels are those orbitals. Okay, the period from left to right. Here, got a periodic table for you. The period left to right tells us the number of energy levels that a particular atom will have in order to hold electrons. So, first period with just hydrogen and helium. Period 1 has 1 energy level. Period 2, because this is the second row, period 2 from lithium all the way to neon, all of those atoms will have 2 energy levels for their electrons. Everything in row 3 or period 3, energy level 3, all the same thing, these will have 3 energy levels to hold their electrons, and so on down the periodic table. So period 1 has 1, 2, 3, 4, 5, 6, 7. Okay, so the left to right, the horizontal rows are periods, and they represent the number of energy levels that any atom will have. There are 4 sublevels within these energy levels. Okay, within the rows, there will be sublevels, and those are shapes. The sublevels are shapes. They have particular shapes, and we'll see what those shapes are. The sublevels have different shapes, and they allow electrons to orbit the nucleus without running into each other. Now, we have letters to represent the orbital shapes. Okay, the letters are S, P, D, and F, and they go in that order. Okay, the S sublevel is the first energy level, or is the first sublevel. P is the second sublevel. D is the third sublevel, and F is the fourth sublevel. Okay, electrons fill up the S, then they'll go to the P's, then the D's, the F's. You'll see how it works in just a sec. All right, so let's talk about their shapes. The S sublevel has only 1 orbital per energy level. Okay, each orbital can hold a maximum of 2 electrons. That's really important. So where is the S sublevel? Okay, whoop, upside down. S sublevel, since it can only hold 2 electrons, is this first, here we go, first row here. Okay, it can hold hydrogen's energy level, or I'm sorry, hydrogen's electron and helium. All right, 2 electrons within that S sublevel. Hydrogen and helium only have 1 sublevel, and it's the S sublevel with 2 electrons in it. It looks like a sphere, looks like a little ball. So the 2 electrons that are in the S sublevel are running around inside, find my eraser, are running around inside that orbital. Okay, trying not to run into each other. P sublevels. So the P sublevels look like little propellers put together like that, little propellers. There's 3 P sublevels. Each orbital, remember, each orbital can hold a maximum of 2 electrons. So if there's 3 sublevels, 3 P orbitals, 2 electrons in each one, there will be 2, 4, 6. So there's 6 electrons total in the P sublevel. This is what the little P sublevels look like. Okay, it says they look like dumbbells. The dumbbells I use at the gym don't look like that. I think they look like little propellers on a plane. So in each of those little orbitals, in this orbital right here, there will be 2 electrons, one there, one there. In this P orbital, there will be an electron here and an electron here. In the final, the third P orbital, there will be an electron here and one here. And those P orbitals fit together just like that. The D sublevel, okay, the D sublevel, there's 5 orbitals within that D sublevel. Each orbital can hold a maximum of 2 electrons. Now that's a theme. You need to keep that in mind. Every orbital, no matter what, can only have 2 electrons. And if the D sublevel has 5 D-shaped orbitals, there will be 2 electrons in each one for a total of 10 electrons that'll fit in that D sublevel. These are illustrations of what the D sublevel will look like. Each of those 5 D orbitals will have a different shape and orientation on the X, Y, and Z axis. You don't really need to know what they look like. You're never going to have to reproduce an orbital shape because they kind of fit together as an electron cloud, and it's really hard to do that anyway. Kind of hard to draw a cloud, you know, with all the ins and outs. Some of you guys are good artists. I did see that on your PowerPoints. You're all about me's. So in these 5 D orbitals, there will be 2 electrons that will fit in each one. So in this first D orbital, there will be 2 electrons floating around through these 4 little shapes. The second D orbital will have 2 electrons, third will have 2 electrons, fourth will have 2 electrons, and fifth will have 2 electrons, for a total of 10 electrons that can fit in that D sublevel. The F sublevel has 7 orbitals per energy level, and it can have a maximum of 2 electrons in each orbital. So the F sublevel will have 14 total electrons. These are kind of funky shaped, funky shaped orbitals, and in each of these orbital shapes, you'll have 2 electrons for a total of 14 electrons. Now, the pattern, hopefully you kind of got it, the pattern was the S has 1 with 2 electrons. The P has 3 orbital shapes, 2 electrons in each for 6 electrons. D has 5 orbital shapes, 10 electrons total. And the F has 7 orbitals with 14 electrons total. So when you look at it, you can see this pattern right here. 1, 3, 5, 7. Okay, it's like your red day. So first energy level, 2 electrons. Or first orbital shape, 2 electrons. The P orbitals will have 3 little orbital shapes, 6 electrons. 5 little orbital shapes, 10 electrons. 7, 14. And we'll put this all together for you, kind of help you out. It does sound complicated, but once I put it together, once I tie it together, it kind of helps. So these are your orbital shapes. There's the S, P, there's the D's, and there's your F's. Okay, great picture. Okay, the structure of these orbitals, I just drew them, but this is how it's going to look. First energy level, or first orbital, will have 2 electrons, and so on. 1, 3, 5, 7 will have 2, 6, 10, and 14. So in that first energy level, so now we're back here talking, I'm going to get a different color for you. Back here we're talking first energy level. Okay, that's the first energy level. Has the S sublevel, because it only can fit 2 electrons anyway. One goes here, one here. Okay, second energy level, it's right here. Okay, second energy level will have an S orbital shape, and it'll have 3 of the P orbital shapes. So here's electron number 1 in the S orbital and 2 in the S orbital. Remember, 2 in the S. Then the P's, here's 2, 4, 6. So there's your 3 P orbitals. Okay, the third energy level has the same thing. It'll have 2 electrons in that s orbital. It'll have sp and ds. The third energy level is big enough to accommodate the s, the p's, and the d's. So it'll have 18 electrons. And the fourth energy level, fourth and beyond, will have a maximum of 32 electrons. Okay, it'll have the s, the f like Frank, f orbital included. Okay, so electron configuration is the arrangement of electrons in an atom. Low energy arrangements are more stable than high energy arrangements. Electrons like stability. Okay, these atoms like to be stable, so they'll fill up in the lowest energy orbital possible. I'm going to show you how to do electron configuration, and what you have to remember is that it's a pattern. You guys have been playing with patterns since you were in kindergarten. I know you can recognize a pattern, so once I teach you this pattern, you'll be able to remember the pattern because it's pretty obvious how it gets set up. So the most stable, lowest energy arrangement of electrons is called an atom's ground state electron configuration. Okay, another one of these goofy principles. The Aufbau principle says that each electron occupies the lowest energy orbital available. Remember, the atoms want low energy. Okay, so the electrons are going to fill in the lowest energy orbital available, which is the s orbital usually, and then it'll fill up. The periodic table shows us where each element's last valence electron is in its ground state. Okay, I know you don't think that yet, but you got to trust me on this. Okay, so on your periodic table that hopefully you were able to print, I want you guys to outline the 4 blocks, the S block, P block, D block, and F block. Here, let me get that up there. That's how I want you guys to draw lines, label each block. That's what I'm trying to spit out. Okay, S block is the first 2 rows on the periodic table. The P block, you skip that middle block. Here, I'm pointing at you. Okay, skip this middle block. All right, the middle block is the D block. Remember, it fills up S first, then the P's, then the D's, and then the F's. All right, just works that way. So remember that in the S block, the S orbital, that little bitty orbital, can only have 2 electrons. 1, 2. 1, 2. I know it's over there. 1, 2, 1, 2, 1, 2. Okay, all of these are S block elements, and all of these will have their valence electrons. We'll have just the 2 valence electrons, 1 or 2 valence electrons in that little s orbital. The P block is over here. Okay, I'm pointing to it over here. P block fills up next, so you'll have 2 electrons here. Then here are these 2, 4, 6 electrons for the P block. D block gets filled next, and then F block after that. Okay, so electron configuration. Electron configuration can be tricky. Got that first one here. I need another color. Let me get my colors here. Okay, so helium. Here's helium. Okay, so here's helium. So when I do electron configuration, I start out with energy level, which is 1, first energy level. This is the S block, and I know helium could be right here. Ooh, look at me do that upside down. There's helium. Okay, first energy level. This is in the S block. Helium is in the S block, and it has 2 electrons. Why does it have 2? It has the one from hydrogen and the one from helium. So the electron configuration for helium is 1s2. Okay, first energy level, S block, second electron that's in there, 1, 2. Okay, let's see. Lithium. Here's lithium. Okay, here's what you do. Once you're done, you know, if I want lithium, you go to, you have to write the electron configuration that comes in front of it, and then the last electron configuration that you stop on will be the one where that element is. So lithium is also in the S block, okay? And it's the first electron, second energy level. So lithium's electron configuration, lithium will be 1s2 because there's electrons in helium, hydrogen and helium, and then 2s1 because lithium is in the second energy level, S block, first electron. You'll get it. Okay, next is beryllium. There's beryllium right there. Beryllium's electron configuration is 1s2, because both of these are filled, 2s2, because there's 2 electrons here, okay? 1s2, that's first energy level, s orbital, 2 electrons, hydrogen and helium. 2s2 means second energy level, s block, 2 electrons. Some of you are going, I almost get it. You will. Okay, boron. Here, let me get a erase and get a different color for you. All right. So boron. Let's find boron. Here we go. Boron, way over here. Is it in the S block? No, it is not. It is in the P block. Okay, so boron's electron, but it's in the second energy level. So boron's electron configuration is 1s2, because these 2 electrons are still filled. 2s2, because both of these electrons are filled. And then we stop on the element that we want. That's the last electron configuration we'll draw. So this is still, boron's still second energy level, but it's in which block? It's in the P block. Is it the first electron? Why, yes it is. That's the electron configuration for boron. 1s2, because both of these are filled. 2s2, okay, if that energy level, or if that first energy level is filled, you go on to the next one. 2s2 is right here. It's filled, you keep going until you get to your element, 2p1. Okay, what's next? Carbon, oh, of course. Okay, carbon's right next to it. So what do you think carbon's is? Okay, 1s2 is filled. 2s2 is filled. Right here. 2p what? 2p2 is filled. Okay, nitrogen right here. 1s2, because both of these electrons are filled. 2s2, because both of these electrons are filled. Go over here, second row. Ooh, I just dropped a marker. Go over the second row, still in the second row. 2, but now I'm in the P block. 1, 2, 3 electrons over. Oxygen, right next to it. What do you think it is? 1s2, because both of these are full. 2s2, because both of these are full. 2p4. Fluorine, right next to it. Oops, here, let me erase. Fluorine is going to be 1s2, 2s2, so there's 1s2, 2s2, 2p5. All right, I think you're getting it. Whether you want to or not, just let it in. All right, neon, get that marker that I dropped. Neon, right here on the end, noble gas. Okay, its electron configuration, first row, 1s2 is filled. Drop down to the second row, 2s2 is filled. What's over here? Second energy level still, P block, all 6 electrons are in there. Okay, it's a noble gas. Sodium, okay, sodium back down here. What do you think sodium is? Let's get a different color for that row. Okay, so for sodium, sodium's right here. 1s2 is filled. Go to the next row. 2s2 is filled. Both of these are filled. We're not to sodium yet. Go over here. 2p6 is filled. Then that means my second row is completely filled, so I go on down to my third row. For sodium, 3s1. Crazy? Perhaps, but it works. Magnesium, right next to it. 1s2, 2s2, 2p6, 3s2. No, I don't expect you to go that fast. I go that fast. I've done it for a while. So that's the electron configuration for magnesium. 1s2 is filled. Go to the next row. 2s2, oop, got a visitor. Hang on. Okay, visitor's gone. We'll pick up where we left off. They were hanging my periodic table, your periodic table. All right, so back where we left off, we were at magnesium, so we're going to go on to our next element. In theory, if my PowerPoint were working, we would be going on to aluminum. There you go. So let's go with orange. So where's aluminum? It's in the third energy level. It's in the P block. All right, and it's the first atom, first electron that's filled there in that 3p area. All right, so electron configuration for aluminum, 1s2, because both of those are full, 2s2, 2p6, go down to the next row because the second energy level is full, go down to the next one, the third energy level, 3s2 is full, and then keep going in the third row, there's aluminum, 3p1. Okay, so this is how these are going to fill up. We'll keep going. All right. I'm not going to do all of them because it'll make the PowerPoint really long. So I'm going to skip through some of them. This would be 3p1, 3p2, 3p3, 3p4, 3p5, and 3p6. Then you would go on to the fourth energy level. So here's fourth energy level. Okay, starts with potassium. Right here, where the transition metals are, this is a tricky spot, okay, right here, because this goes 4s1, 4s2, but then this is the 3D block, okay? The D block is down a row. Instead of it being the 4D block, because it's in the fourth row, it's actually the 3D block. Why? Because elements are put together based on increasing atomic number. And if this orbital, if the d orbital was up a row where it should be, the numbers wouldn't fit together. You would go, sodium has 11 protons, magnesium has 12 protons, and then you go to scandium with like 22. Okay, it's weird. Okay, so in order to keep the atomic numbers in order, that D block is just down a row. There's a lot of things in your life that you have to accept. This can be one of them, okay? So when we're doing the electron configuration for, say, iron, iron's right here, okay? It's in the middle of your transition metals. It's going to be 1s2, first energy level is full. Then you go down the second row. 2s2 is full. 2p6 is full. Then you go down to the next row. 3s2 is full. 3p6 is full. Then you go down to the next row. 4s2 is full. And then where iron is it's 3d, 1, 2, 3, 4, 5, 6. 3d6. Okay? Yes, I realize that says 4s, but then you go back to the 3s. It's okay. All right? That's just the way it is. This will be the 3d block. This will be the 4D block, 5D, 6D. Okay? Down here in the F block is messed up too. Remember how I said fourth energy level will have the S's, the P's, the D's, and the F's? Go back a few slides and you'll see that. Okay? This is 4F. That's 4F. That's 5F. Okay? Again, a lot of things in your life that you have to accept. These blocks are a little bit out of place, but it's okay. It's still the same pattern, okay? They all fill up. Let's keep going. Oh, back. Okay? They all fill up the same way, all right? The pattern keeps going. I wish you were here. I'd do more with you. Okay, so electron configuration for ions. So what we were doing is atoms. An ion is an atom that's lost or gained electrons in order to bond, all right? So ions, we have to be able to do electron configuration for ions. So I'm going to take sodium. I'm not going to do orange anymore. I'm going to pick brown. Sodium is in group 1. Here's sodium. Sodium's in group 1. Ta-da, right there. Sodium will always lose 1 electron in order to have a full valence shell. Well, let me show you its Bohr model and it will make sense. So sodium will have 11 protons and 12-ish neutrons in its nucleus. All right. First energy level will have 2 electrons, hydrogen, helium. Second energy level will have lithium, beryllium, and then boron through neon. Okay, all that can fit in there is 8. Okay, then sodium's right here. Its 1 electron is right here in its valence shell. Okay, 1 valence electron. Group 1 elements, 1 valence electron, right there. In order for sodium to bond, it's going to get rid of that 1 electron. Why? Because when it does, look, has a full valence shell underneath. So it's happy. It's stable. It's more stable losing that 1 electron than it would be keeping it. So when it loses 1 electron, it had 11 protons and 11 electrons in its neutral state. Remember, neutral, pluses equal minuses. All right. It lost an electron. Lost this electron right here. Okay. So it has 10 electrons now. What's the overall charge here? It's got 1 more positive than negative. So this makes sodium with a plus 1 charge because it's got 1 extra plus. Okay? So that is a sodium ion. It always has a plus 1 charge. So to do electron configuration for the sodium ion, get a different color. Okay? That would mean it has 10 electrons. Okay? It's lost an electron. So if its electron configuration was 1s2, 2s2, 2p6, 3s1, if it was like that before it lost the electron, then it loses that 1. It loses this one right here. That's the electron configuration for sodium ion. Okay? Because instead of 11 electrons, it has 10. 2, 4, and 6 is 10. All right. Oxygen always has, will always gain 2 electrons. It's just what oxygen does. So let's find oxygen. I'm going to erase that too. I'll get it on me. Here's oxygen. Okay, there's oxygen. Let's do its First, I'll do a Bohr model for it. Okay, oxygen will have, let's see. I'm just going to do oxygen with 8 neutrons. Okay, 15.999 is 16, so it's 8. So 8 protons, 8 electrons. I need to make that smaller. 8 pluses, 8 neutrals in its nucleus. All right. First energy level, 2 electrons. Second energy level, which is where oxygen is, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 6 valence electrons. Okay, so oxygen always likes to gain 2 electrons. Why? Because when it does, it'll have a full valence shell. Okay, that's why it likes to gain 2 electrons. If oxygen started out with 8 protons and 8 electrons in its neutral state, and it gained 2 more, it would then have 10. All right? What has 10 electrons? Neon. Okay, so the electron configuration for this oxygen ion, oxygen with a -2 charge, because it's got 2 extra negatives, look, do the math, 2 extra negatives, has 2 extra negatives, its electron configuration will be 1s2, 2s2, 2p6. It was 2p4, okay? 4, because it goes p1, p2, p3, p4. But since it gained 2 extra electrons, it will be, here, I'll erase all of that, 2p6. Okay, that's an oxygen ion. Whatever the charge is up here, if it's negative, that means it has 2 extra negative charges. So it has 2 extra electrons. If it's positive, like sodium was, let's say it's magnesium. Magnesium will always have a +2 charge because magnesium likes to lose 2 electrons. When it has a +2 charge, okay, that means that there will be 2 fewer electrons than it had previously in its neutral state. It takes a little bit of practice to work on, so we'll do some of that practice for you, with you. Okay, here's the electron configuration. If you need it, if you look up here at the top, everything is labeled for you. Okay, so let's say I want the electron configuration for chlorine. Okay, chlorine's right here. Okay, so that would be 1s2, 2s2, 2p6. Are we to chlorine yet? No, we're not. So then we go to the next row. 3s2, 3p5. Look, it's in the p5. Third energy level, p5. Okay, let's say we want to do copper. All right, remember I told you that the transition metals were down a row. Look here on the side, you have 3D, there's the 3Ds, 4Ds, 5Ds, 6Ds. So if I want copper, I would do 1s2, 2s2, 2p6, fill up each row, and then go on to the next row until you get to the element that you want. So 2p6, 3s2, 3p6, skip down a row, 4s2, look, we're at the 3Ds, 3d9, 3d9, all right? Let's say we want to do it for rubidium. There's rubidium, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Here's rubidium, we're not there yet, 4s2, 3d10, oh, didn't mean to do that, 4p6, we go down, 5s1. See, it's 5s1. All right, so let's do a few here. All right, we're going to try to do these. I'm going to pause you and pull up my little onboard markers. Okay, got my little board here. Okay, we're going to see if we can't do this. All right, so aluminum. Here's my aluminum. Find it on your periodic table. All right, aluminum. Oh, I'm messing with here. Find it on your periodic table. There's aluminum. Okay, aluminum is going to be 1s2, because first two energy levels are full. 2s2, 2p6. Keep going until you get to aluminum. 3s2, then what? 3p. Where's aluminum? It's at 3p1, right? Okay, so far so good? Here we go. All right, so let's try iron. Iron's a transition metal, and it's in the middle. Okay, so find iron. It's in the first, it's in the 3D block. Okay, so the electron configuration for iron, 1s2, 2s2, 2p6, 3s2, 3p6, go down fourth row, 4s2. Now where's iron? How many over is iron? See, 1, 2, 3, 4, 5, 6. It is 3d6. Okay. All right, bromine. Find bromine. Okay, bromine's in that fourth row all the way over. It's a halogen. So its electron configuration can be a little bit longer. 1s2, 2s2, 2p6, 3s2, 3p6, go down fourth row, 4s2. The whole D block is full, but remember it's 3d10. Okay, go over to bromine. Okay, when you skip over, you go 3Ds, it continues with the fourth energy level. So those are 4Ps starting with gallium. So that will be 4P, and bromine lives at 4P5. Okay. All right, how about that fluorine ion? A fluorine ion, let's see if I can get my pen over here. Fluorine is fluorine with a -1 charge. Why does it have a -1 charge? Well, let me pull up, get the periodic table. If you look at the periodic table, fluorine's way over here. It's a halogen. It has 7 valence electrons. If it follows the octet rule and is going to lose, gain, or share in order to get 8, how many more does it need if it has 7 valence electrons? It needs 1 more. So if it gains 1 electron, it has one extra negative charge, which means it will have a -1 charge, okay, which is what I wrote there. So its electron configuration with an extra electron will be 1s2, 2s2, and instead of 2p5, remember it has an extra electron, it's 2p6. Okay, strontium. Strontium is Sr. That's why I put it on there, because people give me all kinds of weird things for strontium. So strontium is Sr. It's in the second, the alkaline earth metals, about 4 or 5 down. So find strontium. I'm gonna get my pen there. So it is 1s2. Oops, sorry, 2s2, 2p6, 3s2, 3p6, 4s2. 3d10, remember that D block, 4p6. Are we to strontium yet? Almost. It lives at what? 5s2. Okay, nitrogen ion. Okay, nitrogen is in group 5 or group 15, has 5 valence electrons. How many does it need? Well, it needs 8. So is it easier for it to gain 3 or to try to cut loose all 5? Gain 3. So when it gains 3 electrons, it looks like this. Nitrogen, let me see if I can draw on here, with a -3 charge. That's what it looks like, because it gains 3 negative charges. So nitrogen's electron configuration will be 1s2, 2s2, 2p. Instead of 2p3, it gains the 3 electrons, so it's 2p6. Okay, let me go to the next slide. Oop, no, next slide. No, we don't want to save this. There we go. So that's it without my chicken scratch, in case you couldn't read my writing, which I totally don't blame you if you couldn't read my writing. It's kind of hard to write with, but it gets the job done. So what you see here are the electron configurations for each one of these. Okay. You may have done strontium and gone, oh my God, that's going to take forever. Good news, there's a shortcut, but I don't teach you the shortcut until I actually teach you the proper way to do it. So I'll teach you the shortcut on the next slide, because frankly, we've gone on for way too long. You guys have a good afternoon.